So we're going to get that code and run it on a single node. From my node 1, I'm going to do git clone git colon / github.com / jpetazzo, that's me, / orchestration workshop. Oh, I forgot to ask, but did everyone, so can you raise your hand if you managed to log into node 1? And can you raise your hand if it didn't work? No hands? Okay, awesome. So we clone the repo, and then I go into the repo. I see the same files that I had on GitHub. I go to the Docker Coins directory. I have this Docker Compose YAML file. And you know, when you have a Docker Compose YAML file, you know you can do Docker Compose up without even thinking further. It's a little bit like when you have a make file, you can try make, and maybe something will happen. If you have a Vagrant file, you can do Vagrant up. If you have a configure script, there is like ./configure make install. There are a bunch of files like that that kind of tell you something. The Docker Compose YAML file tells you can do Docker Compose up. So we do that. And then it's going to start pulling base images for my application. So there is a Python component here. Then it's installing dependencies with pip. Then it's pulling the Redis image. And then it's going to, oh, now it's getting the Ruby image. Yeah, when I wrote this application, I didn't want to do everything in Python because then the Ruby people would be unhappy about that. I didn't want to do everything in Ruby because then I have the other problem. So I do, a part is in Python, a part is in Ruby, and since some people don't like neither Python nor Ruby, I also have components in other languages. Yep, that's another Python component. And then, surprise, we have some Node components. I don't really recommend that you build your software that way. This is a kind of illustration of, oh, with microservices, you can use the right tool for the right job, or just get the big mix of different things. But here again, like for educational purposes, I like that because even if you, I hope that you will either know one of these 3 languages, or if you know other languages, you can just dive into maybe the Python or the Ruby one, if you want to do some changes and experiment. So this, that thing here, that's the logs of my containers. You can see on the left-hand side what I call the rainbow strip, which is the names of the containers. And on the right-hand side, that's the output of the containers. If I freeze that for a second, I can see that I have, let's see, it's a little bit, yeah. So I have like RNG saying, okay, you got a request on RNG, one on Hasher, another one on RNG, another one on Hasher, and once in a while, the worker says, I've done 4 units of work, and now I'm updating the hash counter, etc., etc. Okay, great. Right, we've been running the application. That's a lot of logs, and we don't want to see them, so I'm going to hit Control-C. When you hit Control-C, you tell Compose in that case, say, hey, can you please stop that app? And so Compose will tell to Docker, hey, can you please stop these containers? And Docker will tell the containers, can you please stop? And by can you please stop, I mean it will send them the term signal. And as with almost every single start-stop script in the Unix world, after a given timeout, if the process, the container, the service, the whatever did not stop, then we send it the kill signal. Because the term signal is like, hey, please stop, but I'm giving you some time so that if you are a web server, you can finish the requests that are in flight. If you are a database engine, you can like flush transactions to disk and whatnot. But don't take too long, because when the sysadmin types reboot, she expects the machine to reboot today, not tomorrow. So after a given time, we kill the containers or the processes or the whatever. So here you could see 2 containers exiting immediately because they were well behaved, and 3 containers exiting after 10 seconds because they were badly written by bad programmers. That's me. So in that case, it's just because the code doesn't do any kind of signal handling. And when it receives the term signal, it's like, yeah, whatever, and it continues to run. And then 10 seconds later, the Docker engine is like, okay, now I kill you. It's a small detail, but I mentioned that because later, when we will do operations like rolling upgrades, rollouts, etc., there are lots of things, like we will see containers kind of lingering around, and like, why is this taking 10 seconds? That's because of that. So by having better signal handling, you can save a little bit of time in deployments, etc. It's 10 seconds we're talking about, so it's not like 10 minutes or anything, but sometimes it can help to understand what's going on. Okay, we are going to restart the app in the background with Docker compose up -d. The -d option is like detached or demonized. It's like with Docker run, you can do Docker run -d to start a container in the background. Now if I do Docker compose ps, this shows me the containers that are running. It's a little bit like Docker ps, but it shows me less information, so it's easier to read, and it shows me only the information for my application. If I'm running other containers on that machine, Docker compose will not show them to me. It also shows me like how the containers are exposed to the outside world. Here I see like my web UI is exposed on port 8000. That's interesting. I'm going to check like what is on that web UI. Let's see if I try curl on my IP address on port 8000. Okay, it redirects me to index.html. You know, let's try this in a browser. So you put the IP address of node 1 in the browser on port 8000, and you see something like this. This is the web UI, and it's telling us how fast we are mining these Docker coins. Okay. All right. So it looks like this is doing 4 hashes per second. It's not. It's looking like 3.333. But for reasons, it shows at like 4440, 440, 440, etc. And then it averages to 3.333 because I can't be trusted with writing front-end code. So now we need to scale that up. We are not happy with those 4 hashes per second. First, because it's not even 4, it's 3.333. And next, because we want, I don't know, at least 20 would be a good target. So how could we scale that? Well, the first thing is that we are not allowed to change the code in any way. We are going to be like the ops team that doesn't, well, I don't want to say doesn't know how to change the code, but it's more like in the contract, no, you are not allowed to change the code. The code has been validated in QA and everything, so you can't go there and do optimizations or whatever. The only thing you can do is start multiple copies of containers and put load balancers and things like that. Okay, so what we could do is we could clone that worker container. So now we would have multiple worker containers, and all of them would be doing like request to RNG and then posting to Hasher and incrementing the counter. And for each copy of worker, things should go faster. If you're not convinced by that, we are going to try it immediately, and it's pretty easy with Compose because there is a scale command. We can do Docker compose scale. Which service, worker, how many, equal to. We do that, and it's super fast. And when we look at the output, yep, now we are doing like 8 hashes per second. Well, it's not 8, it's more like 6.666, but never mind. Well, can we scale farther? Like maybe I can scale to 3. That was fast, and yep, this is going up. That's great. I mean, I just have to scale to 10, and I will have many Docker coins, and we can all go for coffee earlier. And of course, it doesn't work like that. Instead of having between 30 and 40 hashes per second, I seem to be stuck at 10. Maybe I need to put more containers. So I'm going to scale to 20 workers. You don't have to, because spoiler alert, it's not going to be any faster. And I'm going to put to 30, like just for comical effect. We're gonna need a bigger container. So, okay, apparently there is some bottleneck somewhere. We can scale the worker as much as we want, yeah.
When you type in scale worker equals, it realizes that there are already X containers running, and then it adds to that, right?
Yes, absolutely. If I do scale equal X, if I already have enough containers, it does nothing. I mean, yeah, it will do the difference. So for instance, if I do again, like I scale to the same number, like scale worker equals 30, it's like, yep, there's a container number is already achieved. And I can even scale back. If I put a lower number, it's going to kill containers.
Can you scale to 0?
Can I scale to 0? Yes. It's a way to destroy the containers without exactly destroying the service, and it's a concept that can be used in many orchestrators because it's legit in many orchestrators. It's often convenient. For instance, if you have workers that are getting jobs from a queue, sometimes you want to stop the workers, all of them, because there is nothing in the queue, but you don't want to destroy the notion of the worker. So you can scale it to 0 and just clean back up when there are stuff in the queue. Yep, absolutely. Okay, so I'm going to use like some good old Unix tools to find out what's going on. Maybe I'm saturating the CPU or the memory of the machine. So I'm going to use top, and top tells me that I have a kubelet using some CPU time. I have Dockerd, which is highly suspicious. I have this kube controller and a bunch of things. I have Python and Ruby. Now that's our containers. But more importantly, I have 87, like 90% of idle CPU cycles. So this machine seems to be doing nothing for like 90% of the time. We have CPU cycles. Okay. Do we have memory? This tells us that we have 500 megs of free memory over a total of 4 gigs. And if you're not familiar with how memory works in Linux, as long as you have a bunch of free memory here, it means that you're super fine. Because in fact, the real amount of memory used in that machine is indicated here. It's like 1 gig. And then I have 2 gigs and change of buffers and cache. And this memory can usually be reused very quickly. So strictly speaking, I have 500 megs of free memory, which means we have free memory. Like if I add more memory sticks to that EC2 VM, I will just have more free memory and things won't go faster. Okay, maybe it's an I/O problem. Let's use vmstat. And vmstat shows us like SISO means swap in, swap out, and 0, 0. So it means the machine is not swapping, which is not a surprise because we have tons of memory available. And then BIBO is block in, block out. And here there is a small chance like, we have like 100, 200, 400 in BO. Maybe the machine is writing lots of things to disk, and that's the problem. No, 200 is, I think this is sectors per second, so half of kilobytes. So this means that the machine is writing 100 kilobytes per second, which is nothing. And the reason why it's writing is because the output of the containers is caught by the Docker engine, and then it's writing that to log files. So we're generating a bunch of log files, but this is not the thing that is slowing us down.